All right, hello again. It's time for another lecture, and we're going to start out the second part of this course. So hopefully feel pretty good about mechanics now, at least the basics, Newton's laws and momentum and energy, and some even more detailed stuff. But yeah, that's kind of a wrap on that, even though some of those concepts, general concept of motion, energy, those things are definitely going to come back and play a role throughout the rest of the course too. So don't forget all of that, but this is a new part of the course, and so it's kind of different sort of subject matter. We're not worried so much about motion itself anymore, but in this part of the course, it's all about what matter is, what it's made up of, and particularly the atomic nature of matter. So in that whole first part of the course, we kind of just took it as, well, things that are massive or have mass are made of matter. And I mentioned multiple times that that basically just means they're made of atoms, and they have mass. Yeah. So it's the stuff that makes up the universe, the particular stuff. So we're going to explore that stuff a bit more for the first part, or the first kind of beginnings of this part. And then this part of the course is also going to include discussions of heat and, more broadly speaking, things to do with what we call thermodynamics. So temperature, what it means to have for an object to be a certain temperature, how does it increase its temperature, what happens when you increase its temperature, and the different phases of matter, and how things change from one phase to another. So to begin with, we're going to talk about matter and different states of matter, and then after that, when we talk about heat, we start to understand more about how those different kinds of matter or phases of matter go from one to the other, and a lot about energy there too. Cool. So this lecture will include the atomic nature of matter and solids. Each of those are fairly short, so put them together into one lecture. Okay, so before really getting into it, I like this as a quote. Pretty well sums up the concept of atoms and the atomic nature of matter in general, by a guy, Dr. Richard Feynman, very great American physicist. And he said this, he said, "All things are made of atoms, tiny or little particles that move around in perpetual motion, attracting each other when they're a little distance apart and repelling each other when squeezed into one another." So the whole attracting and repelling each other part is a little bit even more detailed than we might go into, but the idea of atoms as these tiny little things that are moving around in perpetual motion is very much something we need to concern ourselves with, but we're going to learn more about. So just a few points on sort of the history of atomic theory, or atomic theory being that matter is made up of tiny little pieces, essentially. It was all the way back in the Greek days. There were atomists back in the Greek days, in ancient Greece, that postulated that things were made up of atoms. Aristotle had ideas that there were elements, sort of earth, air, fire, and water. As we found out, Aristotle may be a great philosopher, not such a great physicist, scientist. But yeah, so this idea of the atom has been around for a very long time, that the world is built out of these tiny little blocks, like tiny little Lego blocks, building blocks that build up to make everything that we see around us. So apparently the idea was a little bit even more refined and further proposed by this guy Dalton in the 1800s. And then finally there's this experiment, this very famous experiment in 1827 by Robert Brown, and he apparently was a botanist, so he was really just observing water, I believe it was water, and, oh, excuse me. And in that water, this is around the time of microscopes were becoming very prevalent and used, I guess. And so when he looked really closely at the water, he saw these tiny little things, these little microorganisms and whatnot that are all in the water. We know, well, you probably know, there's all kinds of stuff in water. Water is generally not just pure H2O, but he saw all these tiny little things in the water, and what was odd was that all those little things seemed to be getting knocked around in these random directions. So things would be here, and then there was no obvious reason that all of a sudden it'd get pushed over to that side, and this thing would get pushed over this side, and this would get pushed over there again. And so he saw this motion, which we now call Brownian motion, and we are able to now attribute it to the actual random motion of the water molecules in that case. So atoms are just these random motions, and we can't see the atoms themselves. They're ridiculously tiny, but you can see the impact they have on slightly larger things. Okay, so a few characteristics of atoms, pretty important, each one of them, to keep in mind as we talk about atoms and matter and the different types of matter. So for one, as I mentioned a couple times, they are incredibly tiny, unimaginably tiny, almost unimaginably tiny. Once you kind of get a feel for scales of things, then, you know, I would say that myself, I have a somewhat reasonable conception of how small an atom is, but only somewhat. It's very hard to imagine how tiny it is. Like, it's the width of a human hair, or even like a blood cell. I believe it's something like there'd be something like 1 billion times smaller than a blood cell. And blood cells are pretty darn tiny if you were trying to look. So besides being incredibly tiny, they're numerous, meaning they're everywhere. There's uncountable billions upon billions upon trillions of them that make up even just the room around you. So there's an unbelievably large amount of them, astronomically large amount of them, or even financially large amount of them. They are also in perpetual motion. Right? So there's essentially these tiny little things, and they're everywhere, and they're constantly jiggling around, or even moving around in larger patterns, but there's always some kind of motion. There's never really a state where an atom is just still. It's always moving around. So that's what we mean by perpetually in motion. And finally, there's this characteristic that we could say that they're ageless, in the sense that if I have a gold atom, say, then 1 million years later, as long as there weren't any nuclear processes that happened, and we'll mention nuclear processes later, but as long as nothing broke that atom apart, there's no sense that the 1,000 years, 1 million years later, that gold atom is any older, right? It's still made up of the same exact parts, and there's no sense that those parts will age in any way. So if you have a gold atom, as long as it doesn't there's no nuclear activity to break it apart or anything like that, it's that same gold atom that time later, it's as if no time has passed for the atom. So that's one way of understanding this ageless. An atom, a particular atom is a particular atom now until, well, like I said, something might happen to break that atom apart, but that's a slightly different thing. As long as the atom is still together, there's no sense that it's gotten any older anyway. It doesn't decay, or it doesn't become decrepit in any way. And yeah, so we have pictures or ideas of what atoms look like. There's a number of different models, ways to think about an atom. One is a fairly simplified or very oversimplified model, which we would call like a planetary model, where essentially, that's like the bottom left image here, there is a central thing, which we call a nucleus, and then around that thing there's these almost like planet-like things orbiting around. Right? So that's one way of thinking about an atom. It's very, very simplified, but it's actually, it's not terrible. Something that might come a little bit closer is not just imagining that there are these nice, well-defined shapes of any real sort, but that it's kind of this fuzzy overall picture. Yeah, kind of up in the right here, and maybe a little bit more, right? But even that's not quite there. We won't really get a good picture of what an atom might look like until towards the end of the course, when we'll talk about quantum physics and how that influenced the understanding of what the atom looks like and how it changes what it looks like, or what it's possible to see when you look at an atom. Okay, so we have atoms. I've just mentioned atoms multiple times, and in the past I've maybe mentioned some of these things: protons, electrons, neutrons. And beyond that, you've probably heard about some of these things before. If you took any sort of basic science class, in chemistry, maybe even in biology, this is sort of the fundamental building blocks. So pretty much any physical science is going to have to tell you about this at some point. And physics being sort of the basic science, certainly we're not going to get around that. So what makes up an atom? Well, like I said in the last slide, there's that central sort of thing in the middle of the atom, which we call the nucleus. And pretty much all of the mass of the atom is confined in that nucleus. All the mass is really just in that middle central area of the atom. So what's in the nucleus? Well, there can be protons and there can be neutrons in the nucleus. And we haven't really discussed electrical charge, and we won't until later in the course as well, but I think you have probably some already idea of what it means to be electrically charged, if you've ever been statically shocked or anything like that. So suffice to say, the protons in the nucleus are positively charged, electrically charged. The neutrons, neutral, they're called neutrons because they're neutrally charged. They don't have an electrical charge. Okay? But that's the nucleus, right? And that's most of the mass of the atom. Now, what's going around the outside of the atom, that makes up sort of these orbits around that nucleus, are the electrons. Right? And the electrons sort of counter the protons in that they're negatively charged, negatively electrically charged. And an electron is very small in mass as compared to the protons and the neutrons. That's why most of the mass of the atom is confined in the nucleus. An electron is roughly a 2,000th the mass of a proton. And like I said about the structure, it turns out since the protons and the neutrons are very contained in this tight little ball sort of in the middle, it's really the electrons that sort of give shape to the atoms. And like I mentioned, we're going to find out a bit later on in this course, towards almost the end of this course, that those structures are what we now call orbitals, and they have various shapes depending on the energy of the electrons there. But yeah, that's basically it. Protons, neutrons, and electrons. And sort of, at least on a simple level, it's like a solar system, right? The sun's in the center of the solar system, that's where most of the mass of the solar system is, and there's planets orbiting around in these far distances. Okay, so what is it that makes up an element then? Right? Because I just told you that atoms are the fundamental building block, and I just told you about the structure of the atoms. But you probably also know that we have things that we call elements, where one atom is distinguished from another atom as being, say, an element, a gold atom versus a hydrogen atom. Okay? So what makes those things different? They're both atoms, but they're different elements. And what it comes down to is really exactly the number of protons in the nucleus of that atom. So if you want to have, say, a hydrogen atom, whatever else is going on in that atom, there needs to be one proton in the nucleus. There can be multiple neutrons, there can be or no neutrons, there could be electrons, one electron, multiple electrons, right? The point is, as long as there's one proton in the nucleus of this atom, that is a hydrogen atom. That's how we define hydrogen. Similarly, helium atom has 2 protons, right? 2 protons in the nucleus. Whatever else is going on with that atom, it doesn't matter, that's a helium atom. There are other names for the, and we'll talk about them in a second. There are different terms for when you change the amount of electrons and the amount of neutrons, but that doesn't change the element that that atom is. And one other example, gold, if you didn't know, has 79 protons. So as long as you have an atom and it has 79 protons in the nucleus, again, no matter what else is going on with that atom, it's a gold atom. That's the gold element. So just some other points. To date, there are about 115 known elements, about 90 of which occur in nature, meaning they can just be found through various natural processes. Others are produced in laboratories by, I think usually by fusion processes or something. I'm not exactly sure off the top of my head. But those atoms or those elements that are produced in the laboratory are generally what we call unstable, meaning they don't stick around for very long. There's a nuclear process that occurs and the atom decays, falls apart, and becomes different atoms or different elements. So as you can see, the word atom and the word element in some cases are interchangeable. If I say I have an atom, you have also some kind of element there, right? So they can kind of be used interchangeably, but the difference is that atom is the much more general term. The element is for the specific number of protons that identifies that atom as a particular element. All right, so this is something you've probably also seen at some point, the periodic table of the elements. And yeah, it's basically, the fact that an element is defined by the number of protons in the nucleus of that atom lets us sort of lay out all the different elements just by, counting up in the number of protons. So the first element in the table is hydrogen with 1 proton. That's up there in the top left of the table. The second element is helium. So go all the way over the top row, just moving across the top row. We got 2 for helium, 2 protons. The third, I'm already somewhat lost. I think it's lithium. The projector's not really good. I can't read that very well. But hopefully you sort of get the idea. There's other things going on in the periodic table, but at the very basic level, it's just laying out the elements by an increasing number of protons. So 1 proton, 2 proton, 2 proton. Yeah. So the number of protons in an atom is what's known as the atomic number. Right? So atomic number is another thing. It's just a way of saying how many protons are in the nucleus of that atom, and in the same way I told you in the last slide, that's saying what that atom is. Right? The atomic number is exactly the number of proton, it tells you exactly what element it is. There's another thing that's usually on the periodic table as well, which is the atomic weight, which, like I said, most of the mass or the weight of the atom is in the nucleus, and the things in the nucleus are the protons and the neutrons. Right? And the protons and the neutrons, it turns out, are very similar in weight. I think the neutrons are just a little bit heavier, but they're very similar. So to get the atomic weight, how much an atom actually weighs, you just add up the number of protons and neutrons in that atom. Yeah. So that's to say that the atomic weight of an atom, of a particular element, can actually vary, right? Because like I told you, it's only the number of protons that make it that particular element. if you vary the number of neutrons, you still have the same element, as long as you have the same number of protons. So the atomic weight can actually vary, and usually the atomic weight that's listed on a periodic table is the atomic weight for the most common, what we call isotope of that atom, I mean the atom that we most commonly find with that number of neutrons. Yeah, not super important, but figured to point out since you've probably seen periodic tables before, get a little bit better of a sense of it now. Yeah. Okay, so like I just mentioned, you can have, there are terms for when you change not the number of protons, because that changes the element, but the number of neutrons and the number of electrons for a particular element. Okay? And in particular, if you change the number of neutrons in the element, meaning you're adding or subtracting, adding or taking away neutrons from the nucleus of the atom, what you're doing is creating different isotopes of that atom. Right? So that's what we call an isotope. It's just varying numbers of neutrons. So for instance, hydrogen, again, hydrogen is one proton, that's what makes it hydrogen, and normally it has 0 neutrons. Right? So there's a picture at the very bottom, hydrogen 1, meaning the hydrogen, and 1 is the atomic weight right next to it, to say that there's just one thing in the nucleus, and that's that proton. So I've hardly ever heard that term. There apparently is a special term for hydrogen 1, usually just called hydrogen, but apparently it's protein. Not that important. These other names are more probably have heard before because they're actually used in different ways. So okay, so you have hydrogen, 1 proton, it has 0 neutrons. Right? So imagine somehow it picks up a neutron. Somehow a neutron gets pulled into the nucleus, and now you have a hydrogen element still with 1 proton, but now you have 1 neutron, and you still have an electron. Right? So this is what we would say an isotope of hydrogen, and particularly hydrogen 2, 2 meaning the atomic weight again, so 1 proton, 1 neutron, pretty much the same weight, so we just call it 2. And this term you might have heard before, deuterium, is actually used. Deuterium is another, or another more colloquial term is heavy water. And yeah, so, and then finally you could add even, you could keep adding more neutrons, but there's actually, if you have a hydrogen atom with 2 neutrons in it, this is another particular isotope of hydrogen you might have heard of before. We would have hydrogen 3, so proton, neutron, neutron, atomic weight 3. Also called tritium. So tritium, it turns out, is a radioactive element, so whenever there's some sort of radioactive incident back in, well, I don't even know when it was, but I won't date myself too much, but whenever there's some sort of radioactive incident, so a meltdown or things like that, oftentimes you might hear about tritium because that is something that might get produced in that sort of environment and is radioactive in such a way that is rather dangerous. So these isotopes of hydrogen are very sort of special enough, common enough that they get their own names. Most of the time, if you're talking about an isotope of something, you're just using more of this like hydrogen 1, hydrogen 2, hydrogen 3. Like if you have an isotope of carbon, like carbon 14, carbon 15, carbon 16, you don't usually get special names just for each isotope. But hydrogen is pretty special in itself. So we get some nice names. Okay, so finally the other thing we can do with atoms and still have the same element. Okay. So again, remember keeping proton, same number of protons is the same element. Then we just saw if you change the number of neutrons, you get isotopes of that element. If you change the number of electrons so that they don't balance out the number of protons, then we get what's called an ion. It's an electrically charged version of that element. So recall that protons are positively charged, electrically positively charged. Electrons are negatively charged. So in a usual case, an atom or a particular element will have the same number of protons as it has electrons, meaning that there's some amount of plus charges and there's an equal amount of minus charges, and they overlap. There's protons and electrons, and so overall there's no net charge. The same amount of pluses as you do minuses, they balance each other out, and the atom is electrically neutral. So for instance, if you have chlorine, chlorine is 17, atomic number 17, meaning it has 17 protons in the nucleus, and it normally has 17 electrons, right? 17 pluses plus 17 minuses is 0, no net charge. However, if chlorine were to pick up an extra electron somewhere, you would have one extra negative than you did positive overall, and so now we would have a negatively charged atom of chlorine. So we go from this picture on the bottom left where you have chlorine, 17 protons, 17 electrons, somehow picks up an extra electron. We now have 17 protons, 18 electrons. Overall, this is now a negatively charged chlorine, right? An ion, negatively charged ion of chlorine. And the opposite sort of thing can happen too if you have, start out with a neutral atom, say sodium this time, where you have 11 protons, 11 electrons, overall 0 electrical charge, same amount of pluses and minuses. But sodium might give off an electron to somewhere else. It might lose an electron in some way, meaning now it has one more positive charge than it did a negative charge. So now this is a positively charged ion of sodium. And in these examples, it's only one electron losing and one electron gaining, but that's not the extent of it. You can lose multiple electrons, you can gain multiple electrons. So you could have multiply charged ions. Well, it's either going to be multiply negatively charged or multiply positively charged, because it's really the net amount of electrical charge that's telling you what the charge of that atom is. So yeah, so basically if you have an excess of electrons, being more than the protons, you're going to have a negative ion. And if you have a deficiency of electrons, meaning you have more protons than electrons, you're going to have a positively charged ion. Cool, so that's the basis of, for atoms, pretty much in general, like the basics of atoms, structures, what can happen to an atom, right? If you change protons, then you're changing elements. If you change neutrons, then you're getting isotopes. If you change electrons, you're getting ions. So those are all the different sort of ways you change atoms. Now, what happens, right? I said atoms are these building blocks. So what atoms will do is they'll combine together, they'll bond together in different ways. We're not going to worry, in a chemistry class you would worry more about how they're actually bonding and the types of bonds, but we're just getting a very brief overview. So they combine together, they sort of interlock together in certain ways. And when that happens, when two or more atoms bond together, we call that a molecule. And they don't need to be different kinds of atoms, right? So for instance, if you have two hydrogen atoms, or sorry, two oxygen atoms, and they bind together, then we have O2, and that's a molecule, right? Two of the same kind of atom, but it's two or more atoms together, so we have a molecule here. This is called dioxygen, or sometimes gaseous oxygen. This is the standard form of oxygen that's actually in the atmosphere. It's not just single oxygen, it's O2. Other examples are, say, ammonia, which is nitrogen and 3 hydrogens, right? So definitely 2 or more atoms. And I think that's the second picture here. You have a nitrogen atom, and then you have these 3 hydrogen atoms that are bonded to that nitrogen atom, and we get a molecule that is ammonia. The other one on here, very common, very extremely important in our world, is H2O, right? Water in the liquid form. But H2O is two hydrogens and bound to an oxygen, and we get a molecule of H2O. And I don't have the fourth one written down. That would be CH4 or H4C. That might be methane? I'm not sure, I'm guessing. Doesn't matter. Okay. So like I mentioned, in chemistry, you're mostly concerned with molecules that are combining with other molecules, or molecules that are breaking apart into individual atoms, or atoms coming together to form molecules. So these are all chemical processes. Or another way of putting that is, in a chemical reaction or a chemical process, all that's happening is you're rearranging the atoms to form different molecules, or sometimes, like I said, to just break molecules down into the individual atoms. So really, it's a rearranging of atoms. Right? So we're taking those building blocks, rearranging them around in some way. Right? Those are chemical processes. And if you want to, for example, if you want to pull apart a molecule, you need to put in some energy. So, for instance, in photosynthesis, the thing that plants do in order to produce energy, they actually utilize sunlight, the energy from the sun, to break the bonds of carbon dioxide into the individual carbon and O2 dioxide, or O2. And then on the other side, if you're combining atoms together, you're generally releasing energy. So, for instance, when oxygen combines with iron atoms, it forms rust. So that's what rust is. If you didn't know, it's oxygen from the air initiating a sort of chemical reaction with iron in steel, or just raw iron, or any sort of iron alloy, and forming a compound, rust. I don't know what the chemical compound rust is, but something with C and C's and O's. Oh no, something with iron, Fe and O's. The important part, though, is that in a chemical reaction, we don't actually change the kind of atoms that we're dealing with, right? So if you start out with gold, you're going to end up with gold somewhere. If you start out with carbon, you're going to end up with carbon somewhere, right? The same elements that we start out with are the elements we end up with. They're just rearranged. Okay? Rearranging those building blocks. And just as then a preview, since it sort of naturally leads into this, but later on in the course, when we talk about modern physics and a little bit more in depth about nuclear physics, say more about this. But if we have a process that changes the structure of the atom, or changes one atom, a type of atom, to a different type of atom, that is when we get what we call nuclear processes. So it's not just moving atoms around, it's rearranging the pieces inside of the atom. So rearranging, adding protons, or smashing two protons together to form a proton, and enough energy comes up to make the other one into a neutron. Or some other times, this chart here is an example of what we call fusion, where you're basically smashing the bits, the pieces that make up atoms together, or smashing atoms overall together, and actually changing the structure of those atoms, the internal structure of those atoms. There's other sort of process, nuclear process, which is called fission, which is when nuclei or atoms essentially break apart and become other atoms, other types of elements too. So yeah, so we'll talk about this more later on. This process in particular is incredibly important for life in, well, in our solar system for sure. If there is life elsewhere, it's probably important for that too, because this is the major process that drives our sun. It's this hydrogen helium sort of fusion chain. Yeah, so more about that a bit later on. Cool. So that was all I had to say exactly about atoms in particular, but keep in mind that that idea of atoms, the little tiny things that are in perpetual motion, are numerous and all that different stuff, is underpinning pretty much the rest of this part of the course. Right? So the idea of atoms as these tiny little things that are just jiggling around is very important to keep in mind, and we'll probably be referring to it constantly. That said, we're going to talk about the first phase or state of matter, not really first in a chronological or particular order, just the first one we're going to talk about, but that is what we call solids. Alright, so what is a solid? Well, a solid, there's a number of ways you could be more detailed in defining these things, but we're going to give sort of basic properties and just kind of work with that. So a solid is something that has a definite shape, has a definite size, like that rock. It is incompressible, meaning if you squeeze it or try to squeeze it, then you might change the shape of it, but you're not pushing the atoms that make it up any closer together, really. There might be some little bit of give, but it's at least nearly incompressible. And yeah, so the atoms, right, going back to this idea of the atoms, the tiny little bits that make up this solid, are arranged in structures that don't really change. Right? The atoms themselves are moving around, but the overall structure remains the same. So that's partly what makes that solid a solid. And there are two sort of main classes of solids. One would be what we call a crystal or crystalline solid, and that is where the atoms that are making up that solid are in these nice rows and columns and form into these very clean, nice geometric sort of shapes. Right? So table salt is one type of thing that forms this crystalline solid. The other type is what we call amorphous, meaning that the atoms that make up the structure of it, there's no particular pattern to the way they're arranged. Right? So in the picture here, you have the atoms, or the particles, or molecules, whatever it is that makes them up, are in these nice sort of rows, stacked all on each other. Now move down to the other picture, you have the atoms that make up this amorphous solid. They're pretty much sort of randomly strewn about. There's no overall structure to them. And cotton candy is an example of an amorphous solid. But again, table salt, cotton candy, they both hold up their own shape. They have a particular size, and they, you could stand them up on their own. Okay, so a question for you to think about is, what would you say if I asked you which is heavier, iron or cork? Like iron nail or bag of cork? Or just a piece of iron, piece of cork. Well, if you thought about it, it sort of depends, right? It actually depends on how much each of those things you have, right? Like, for instance, if I did just have a small little nail and I had a big bag of corks made up of cork, the cork's probably going to weigh more than the nail. Right? Does that mean that that cork is heavier than iron in a general sense? No. So oftentimes when you say you want to say compare materials, like how heavy one material is than the other one. More what you're asking is how dense is that material? What's the density of those materials? And so if we want to compare how heavy something is or how dense something is, we need to compare the same volume of material. So for instance, if you have that small nail and then somehow whittled away one of those corks into the same size as that nail, then we could compare sort of apples to apples, the same volume of each, and the nail would be heavier because the nail is a more dense, that iron is a more dense material. So it turns out when we're talking about solids, this property of density is fairly fundamental. So density of a material is, well, this is the equation. You could also say density of a material is proportional to the amount of mass of that material and inversely proportional to the volume of the material that you have, the amount of material you have. So in this way, it doesn't actually depend on the particular amount of material you have. Like if I have 10 kilograms of something and it takes up, I don't know, a liter of space, then if I had 100 kilograms of that, it would take up 10 liters of space. So these things, the density of the material itself is what remains constant regardless of how much of the thing you have. So if we're going to measure density, you can measure it in a number of different ways, but I think for the most part we're going to look at it as grams per cubic centimeter. So grams is just another, is the standard basic standard metric measurement for mass. Oftentimes I've said kilograms, but kilograms is 1,000 grams. Gram is kind of the more basic thing. And volume in our case, we're going to measure in cubic centimeters. So cubic centimeter, a centimeter is about, it's a little less than half of an inch. So a cubic centimeter is like a cube, sort of like that size. Okay. So a gram per cubic centimeter, and we just have some examples of the density of different materials. And well, as it turns out, one that's might stand out to you is water. So pure water, pure H2O, is 1 gram per cubic centimeter. This is not an accident. Water is one of the defining quantities or defining materials for density. Right? So the density of material, it would sort of define 1 gram per cubic centimeter is, that's what water is when you have pure water. And a little bit more detail, but technically that's a particular temperature and a particular pressure too. But I'm not going to worry too much about that right now. Right? So suffice to say, if you have 1 gram or 1 cubic centimeter of pure water, it would weigh 1 gram. Right? That's what it means for water to have a density of 1 gram per cubic centimeter. So you compare that with some of these other materials. Mercury, those are also given the liquid form of mercury, is 13 grams, over 13.5 grams per cubic centimeter. So a lot denser than water. Over 13 times more dense than water. Versus if you look at some of these other materials are given as their density when they're solids. So, well, gold has the highest density, 19.3 grams per cubic centimeter. And another way of saying that is if you had the same volume of each of these things, if you had 1 cubic centimeter or a cubic foot, if you had the same volume of all these things, the gold is going to weigh the most because it's the densest. And the cork is going to weigh the least. It's only 0.2 grams per cubic centimeter. Versus the lead and the iron, right? So just some examples of different densities. So what does density depend on? caught my throat there. All right, so the density of material, right, it's a fundamental thing to the type of material it is, so hopefully it makes sense that it depends on essentially the atoms that make up that material, right? Because the atoms are what are making up like the substance of the material, so the density would make sense to depend on that. And even more, in more detail, the density of the material is going to depend on the mass of the individual atoms that make up that material. So more material is made up of more massive atoms, right? Atoms that have more protons that make it up and more neutrons in the nucleus is going to be a denser material in general. It also depends on the spacing between the atoms in that material. So if you have some atoms that are making material, remember there's tons of them and they're all kind of jiggling around, but in solids they're jiggling around sort of in place, they don't really, the overall structure stays the same. And if you have atoms overall and they're generally about this far apart, that material is going to be a certain density, versus if the atoms overall are much closer, that material is going to be more dense overall, because it's just more, it's more matter that's making up that material, right, in the same volume. And again, so the density is just the property of material. It doesn't depend on how much material you have. It depends on the fundamental atomic sort of structure of that material. So some examples of materials, right? If you have aluminum, you have a chunk of aluminum is atomic number 13, meaning it has 13 protons in the nucleus of it. And largely, being most commonly, aluminum has 14 neutrons. It weighs, its atomic weight is 27, its density is about 2.7 grams per cubic centimeter. So an atom that has 13 protons and 14 neutrons, density is about 2.7 grams per cubic centimeter. As opposed to, if you look at lead, lead is atomic number 82, meaning again 82 protons in the nucleus, and the most common form of lead, isotope of lead, is 126 neutrons. Right? So its atomic weight is actually 208. Its density is 11.3 grams per cubic centimeter. So this is only really an example of the individual mass of the atoms making up the material, ending up producing a much more dense material. So you have a material that has essentially 27 things making up the nucleus of it, and its density is about 2.5, a little over 2.5 grams per cubic centimeter, versus something that has 208 things making up the nucleus of it. That one is about over 11 grams per cubic centimeter. So the individual mass of each of the atoms making the material more dense overall. This is not an example of the spacing between the atoms making a difference in density. Well, there's probably that going on there too, but all I'm pointing out here is that differing masses of the atoms will make it more dense material, more or less dense material. Alright, so let's just walk through calculating what the density of a material is. So suppose that you're given a block of some material, you're told it's gold, and we want to verify that it's gold. Well, how do we verify it's gold? We calculate, measure, and then calculate its density, and compare that to the density we know that gold is. So if we have a block, and say we measure the dimensions of it, it's a rectangular block, so all we got to do is measure the height, depth, and the width. We get this maybe 20.5 centimeters wide, 10 centimeters deep, and 5 centimeters high. Multiply all of those together, we get a volume of 1,025 cubic centimeters. And then we go ahead and measure the mass of that brick, put it on a scale, a calibrated scale, and then we find out that that mass is, say, 11,600 grams. Well, remember, density is mass divided by volume. So you take the mass, divide by the volume, And what do you know? We get 11.3 grams per cubic centimeter. Which, if we look back, that is not gold, right? 11.3 grams per cubic centimeter is the density of lead. So if somebody gave you a brick and told you it was gold, you found out that that was the density, they were lying to you, right? Gold is much denser than that. All right, so say this person, somebody who gave you that gold brick beforehand, you found out it was lead, weren't very happy about that. They try to make it up by giving you something else and telling you it's gold, right? And maybe they've gotten a little bit wise, so they didn't give you a straight brick and you can easily figure out the volume. So they think maybe you won't discover that they're trying to cheat you again. In that case, it turns out there's another very useful way of figuring out the volume of any material, as long as you have a big enough container, and you essentially take that container and calibrate it, meaning you put marks on it to show how many, say, liters or cubic centimeters of water it takes to fill up to those certain levels, right? So all these, we call graduated cylinders, meaning if the liquid's up to that first line, then it's 1 cubic centimeter. It's up to here, it's 7 cubic centimeters. Right? So we have this container, and you put some water in it, and notice the first level, say it starts out at 7 cubic centimeters. Then we take our material, whatever they gave us, put it into that container as well, and that material, essentially the volume of that material, when you put it in, is going to displace the same volume of water as it is, right? So you put in whatever amount that is, it's going to displace that water, meaning it's going to raise the water level up, and however much that water level raised up is the volume you just put in. So if it goes up from 7 to 9 cubic centimeters, then what do you know? It's 2 cubic centimeters. Right? That was the volume of that chunk of material we just put in. So, very good for you, you've outsmarted them, figured out that we could discover the volume of this irregular shaped thing, then its volume is 2 cubic centimeters. Again, we take it to our little scale, measure it, the weight of it, or the mass of it, it's 10 grams, figure out the density, 10 divided by 2 is 5 grams per cubic centimeter. So once again, those darn fool's gold people, well, you're trying to get fooled again, because 5 grams per cubic centimeter, remember gold is almost 20 grams per cubic centimeter, so this is almost a little more than a quarter of what the density of real gold is. This is an example of what we call fool's gold, or iron ore, iron pyrite, something like that, which is actually just iron and sulfur. Kind of looks like gold. Alright, so let's wrap this up with a couple of questions you can hopefully answer on your own. And this all has to do with water and taking all that we already know about density and how density is calculated as the mass of something divided by its volume. One other thing maybe to point out here is that a liter is another measurement of volume. 1,000, I believe it's 1,000 cubic centimeters is a liter. So a liter is just a measurement for a larger volume than cubic centimeters like this, a liter, maybe more like that. Right, so given this information, given that only the fact that water expands when it freezes, meaning its volume gets larger when it freezes and becomes ice, can we answer these different questions about it? Yeah, so hopefully pause, take a minute, try to think about these things, think it through, and come up with some answers. All right. So let's think about this, right? Trying to compare a kilogram of ice and a kilogram of water. Right? So from the whole last, well, not the whole last section, but the last section talking about how much mass something has is literally saying how much stuff is making it up, right? So if we're talking about pure water and it's a kilogram, then that is however many trillions of H2O molecules, right? That's all that it is. Which one's going to have more volume? If you have a kilogram, some number of H2O molecules in that solid form versus some number of H2O molecules in that liquid form, right? It's the same number of them, it's the same mass, it's made of the same atoms, but given that water expands when it freezes, its volume grows when it freezes. So 1 kilogram of ice is going to be a little bit bigger, take up a little bit more volume than a kilogram of water. Right? So that's why ice is the answer to the first one. Which has more mass? Well, hopefully from what I just said a minute ago, you realize that they are the same, right? To say something is a kilogram is to say it's what its mass is. So if I have a kilogram of ice, I have a kilogram of water, I have the same mass of these things, right? Because I have the same number of H2O molecules in each of these things. I need a dish for the water, the ice I can hold. Which has a higher density, ice or water? Or is it the same? So if we want to think about it as a higher density, well, remember that density is mass divided by volume. So if we take the same mass, we take a kilogram, we divide it by the volume of water, and then think about then dividing by the volume of the ice. And remember the volume of the ice is a little bit bigger than the volume of the water. Right? So when you're calculating the density of the ice, the denominator is slightly larger, right? Meaning the overall density is lower. Or another way of saying that is that when you're calculating with the water, the denominator is a little bit smaller than it is with the ice. So a smaller denominator means larger number overall. The density for water is larger. Or you could say water is more dense than ice. Which of these then will have more mass? A liter of ice or a liter of water? And like I said, a liter is a measurement of volume, right? So if you have the same volume of ice as you do water now, we're not talking about the same mass anymore, we're talking about the same volume. The one that's more dense, the more dense material is going to be the one that weighs more. So, water, right? The liter of water is actually heavier than a liter of ice. Cool. And just to point out that ice and water are actually fairly unusual in this way. Most materials, right, so this is when you have a liquid, that water, and it freezes, it becomes a solid. Most of the time, materials contract when they freeze, they get a little bit smaller. However, water is very unusual in that it expands a little bit as it freezes. It is an incredibly useful, strange thing, because without ice being less dense or expanding as it freezes, we wouldn't, well, life on Earth might not exist the way it does, that's for sure. So this is actually pretty unusual for a material, but ice, water, steam. H2O is a very kind of particular thing, and we're all lucky that it is. Yeah. Cool. So that's it for this lecture. That's it for solids. Next time we're going to be talking about liquids. and I will see you then.